Okay, welcome everybody to this week's installment of the California Dreams Technical Webinar Series. We've got lots of things going on in the hub as always, including today's seminar. Today we are very excited to have presenting to us Florian Herrault from PseudolithIC in the Santa Barbara area. Florian and PseudolithIC are a semiconductor startup revolutionizing RFIC design, combining compound semiconductor with silicon in a exciting technology for heterogeneous integration. Florian has over 30 patents in the area, was at HRL for a number of years before joining PseudolithIC as a co-founder. He's currently the CEO of PseudolithIC, and we're very excited to have him presenting today. So with that, I will turn it over to Florian.
Yeah, thank you, Steve, for the introduction. And since effectively you mentioned everything I wanted to say on my first slide, let me just jump into the outline right away. Really excited to be here and obviously have the opportunity to represent PseudolithIC and be part of the California Dreams Hub and this great technical seminar series. I figured most of you don't know about PseudolithIC, so I was going to spend a few minutes talking about the team and our capabilities and our vision, and then dive into really what we're focused on today, which are RFIC chips for millimeter wave communications, and why we think hybrid manufacturing and heterogeneous integration are key to the deployment of commercial solutions. Hopefully, you'll be interested in hearing about the manufacturing technology that we're actually developing and our IP in this co-integration techniques and why we think the PseudolithIC way is the right way. And then I'll end with talking about some of the design examples. So we'll go through a series of microscope images of the circuits that we've built, along with S-parameter plots and power measurements and noise figure measurements, and try to convince you that we're building the blocks to develop these commercial chipsets in the near future, and dive into a little bit of how we think CMOS provide unique value when combined intimately with compound semiconductors at the chip level to build effectively system on a chip. So I look forward to going through the presentation and answering your questions at the end. Okay, so who are we and what's our vision? Well, hopefully you understand that we want to develop the smartest heterogeneous RFICs in the world by combining CMOS functionalities and intelligence from analog, mixed signal, and digital blocks with the best-in-class performance for RF components using compound semiconductor transistor chiplets. So our chiplets, as you'll see, are not these large silicon chiplets that you hear about in the news. These are microscopic transistor chips where we can yield many per wafer and integrate those into a low-cost, commercial 200 millimeter diameter silicon platform, which allows us to build this CMOS intelligence, these RF blocks, and effectively scale up to commercial volume. So the team is really now about 15 people. You'll see a photo of the team soon. We founded the company in 2021, so we're about 4 years old. Took and started with government contracts. So thanks to the several organizations that are represented here, from NSF to DARPA and others, that have really helped us develop our concept, demonstrate first proof of life, validate the technology, and really try to transition it into defense and commercial applications. To accelerate commercialization, we decided to take a seed investment in 2024, led by Entrada Ventures and supported by Encore Capital and Foothill. Great investors. If any of you guys have questions, happy to talk about those guys. Obviously, please allow me to talk about my co-founder and chief technical officer, Jim Buckwalter. I'm sure many of you who work on the RF domain knows him very well. He is obviously focused on circuit design architectures, both in the silicon and compound semiconductors, and leading the design and test team and the product development at PseudolithIC. Over the last few months, we've actually been fortunate to have a couple of press articles. One is in compound semiconductors, Microwave Journal gave us the opportunity to be on the cover just before IMS, and they played on the chiplet and chiclet concept. For those of you who like candy, that might remember. If you come by the office, we've got a bunch of those now in a bowl. And then more recently, Semiconductor Give You a Review magazine gave us the Heterogeneous Integration Technology of the Year award, which was a fun recognition for the people on our team who work hard to develop the process, control it, mature it, and effectively test circuits, on a weekly basis. So these are all, industry recognition that we obviously are grateful for. We have built obviously our patent portfolio over the past few years around circuit design architecture that really take advantage of this heterogeneous integration technology, as well as a manufacturing IP, obviously. So we've got 8 issued patents today and several in the pipeline as well. And as I mentioned, effectively, a strength of our company is this full stack solution from design to test and manufacturing at a very rapid pace. We do this because we're able to effectively store compound semiconductor chiplets on the shelf from these wafer runs and integrate them very quickly into new silicon IC designs. We'll talk a little bit throughout the presentation about our EDA environment, our process technology, and our test and results. So I'm not going to spend much more time on this slide, but if you have any questions about the details, let me know right there. And this is a team, friends and family, actually, at a recent bowling event. 15 people, several of them are remote. We have about maybe we have 3 people remote today who are significant contributors of the team as well. And hopefully you guys cannot zoom in and look at the bowling scores, but hopefully, we are better at our work than we are better at bowling, I guess, and I'll leave it at that. But it was a fun event. And then, as Steve mentioned, we are located in Santa Barbara. So I did want to highlight a little bit about the local ecosystem and how we have greatly benefited from it in the first 4 years of the company. First and foremost, obviously, UCSB has state-of-the-art microelectronics capabilities in microfabrication and semiconductors, in test, and so on. So we access those with an industry rate. When we started the company, we joined the UCSB CNSI Startup Incubator. I put the link here. It's obviously available online. And the people running the show over there are wonderful. We were able to obviously get lab space, desk space, as well as access to the resources for the first 2 years, which allowed us to really get started effectively. More recently, they've developed a cleanroom technician program and an equipment maintenance training program. And I think this is well known within the hub as well. UCSB was really one of the pioneers to do this. And we've participated in some of their events, but we've also hired people who took these programs to great benefit to PseudolithIC. So, as we talk about workforce development, especially locally for us, this is one of the key stepping stones that is helping us manufacture our chips today. We've also hired some interns for the summer from Santa Barbara Community College, and I've taken advantage of the California Dreams Hub project opportunities through some of the multi-project wafer runs in compound semiconductors that have been offered or are being offered so far to supply our chiplets effectively. So as you can see, we're really embracing the local ecosystem and the creation of the hub and hope to continue to participate and strengthen it with our approach and our technology. Okay, now that hopefully I've set the stage around PseudolithIC, let me dive into our RFIC technology and millimeter wave communication. So some of you are probably very familiar with this. And, I think the point of this slide is really to say, well, look, the talk of the town is AI, data centers, photonics, and it's all true, and it's all well-deserved, and it's all critical for the future of technology. But today, RF chips are everywhere, right? You have some in your pocket right now, on your desk. your street next to it, your tower, etc. And really, it's only going to continue to grow, right? Obviously, we need more data bandwidth, we need more power, and we need better transmission. And today, I think whether it's in satellite communication, next generation base stations, or even emerging applications, the need for RF chips is continuously growing. I picked one marketing example around this on phased arrays. This is projections around millimeter wave beamformers market size in the next, I guess, 8 years. And what you can see is you're talking about tens of billions of dollars in satellite communication, cellular infrastructure, radars, both for commercial and military applications. And today, effectively, as I'll mention on the next couple of slides, there is really a cost limitation to using high performance RF front ends such as GaN amplifier in a phased array because the cost per element is so high, right? So in a phased array structure, each element consists of at least one antenna and one RF transmitter or front end. The beamformer on the back end can be done in CMOS, usually using multiple channels per chip. And what we see is that the cost of GaN is just too high. And so hopefully, PseudolithIC's vision is to integrate GaN level performance at the CMOS level cost, right? And being able to enable the deployment of these new solutions for communication, both at the volume for defense applications, but also high volume commercials. And really, this is the 3D vision, right? What the commercial phased array might look like in the future. You would have a CMOS beamformer coupled to a backend PCB on a heatsink, interfaced on a laminate with the RF front end, which would consist maybe of a GaN power amplifier for the power density and efficiency on the transmit side, and an indium phosphide LNA on the receive for its sensitivity and low noise figure. Both coupled to maybe a switch, but also an antenna layer with a lambda over 2 spacing. As the frequency increases, the space becomes tighter, but yet and therefore the heat dissipation usually become higher, but you also want to be able to pack a lot of functionalities into the same thing. As I'll show in the next slide, what we see is, beamformer IC have increased in functionalities, increased in performance, lowered in cost, and have really become almost commoditized today. On the other hand, 3.5 solutions are still very much a niche application, especially for high performance, such as GaN and indium phosphide, and low level of integration. So unless we find a better way to do this, the high volume millimeter wave phased arrays will probably won't exist commercially for quite some time. And this is another example, right? So if you build a semiconductor chip in gallium nitride today, your amplifier will look very similar to what it looked like 20 years ago, although maybe back then it was made in gallium arsenide, but you have a multi-stage design where you amplify your RF in to your RF out, and then that's about it. On the other hand, in the silicon industry, the level of functionality and integration has scaled dramatically, right? So you go from RF mixed signal all the way down to digital, antenna to bits, all in the same chip. And those are produced at very high yield commercially today and work wonderfully. So can we take the best of both worlds and take the performance of the GaN and integrate it into a solution that is high level of integration in a silicon platform? And to further reinforce this technical challenge, we have the silicon nodes performance is actually dropping, right? So even though the level of integration increases, the cost goes up, but the RF CMOS performance goes down. In contrast, GaN and indium phosphide are outperforming in terms of power density and efficiency and etc. But those are high cost and low level of integration. So effectively, all of those should convince you that heterogeneous integration is required. It's not just a nice to have, it's really needed for the future RF front end and especially for commercial phased arrays. This is an example, right, where you could combine a different illustration, where you combine different technologies on the transmit and receive side, all the way from your DAC and ADC to your antenna. A second value is that instead of developing expensive monolithic solutions, sequentially, we can quickly trade performance and cost and adjust our value proposition through heterogeneous integration and develop the best solution for the market without reinventing everything every time. Okay, so setting the stage, now let me dive down into the manufacturing advantages of the PseudolithIC process for chiplet integration. So I've talked about RF circuits a minute ago. This is what an RF chip looks like. This is an RF amplifier if you haven't seen one before. This is a Google image, so I'm not sure who designed it or whose fab was used, but all are pretty similar. And what I've tried to highlight here is the number of transistor cells. So this isn't a silicon digital chip, right? In an RF amplifier, you have a handful of transistor cells. Everything else is made of transistor, capacitors, resistors, transmission lines, and inductors, so all passive elements. So think about this, right? You're using a small diameter wafer that is expensive. Maybe it's silicon carbide. You grow an expensive gallium nitride epitaxy on top, and then you barely use 10% of it to make the high value component, the transistor. Everything else is pretty routine. So now if you can decouple those passive elements into a low-cost substrate, you can completely change the manufacturing paradigm and manufacturing cost model of these technologies. Just use what each wafer is good for. So this is really the PseudolithIC way. And then let me dive into this. So effectively, we start with the best RF materials. So silicon SOI for circuits and compound semiconductors for transistors. So on the bottom right-hand side, you see a compound semiconductor wafer. This one specifically is a gallium nitride on silicon carbide, 4-inch in diameter. And what we do is we only build transistors. So per wafer, one can yield over 50,000 transistor cells per wafer. We call these chiplets, right? They're microscopic chips, roughly 200 microns on the side. And what we see is the yield goes really high, really high, because now you repeat the same structure everywhere. So the manufacturing efficiency of each wafer is really high. And I highlight this in a few minutes with a couple of cartoons to really drive the concept home to you guys. On the other hand, all of the circuit architectures are built in our silicon SOI CMOS platform. So there is simple blocks like the amplifier circuitry, right? Matching networks, power combining, DC biasing element, blocking caps, RF in, RF out, etc. Second, what we add as a special sauce is this CMOS intelligence, where we can build power detectors, ESD, current sensors, current monitoring, etc., and being able to effectively develop an intelligent GaN amplifier or indium phosphide amplifier. And then we do this on a scalable, high-volume commercial platform. We use a 130 nanometer RF SOI platform today, or a passive high resistivity silicon interposer. Those are very low cost in compared to high-end RF silicon or compound semiconductor. So we're able to tape out very frequently, effectively every other month, or maybe sometimes quicker, in our silicon platforms to iterate or develop new circuits in the same wafer. That's really our design IP. Although those compound semiconductors are expensive, we're really driving down the cost of these transistors. And I wanted to give you this chart because these are costs and volumes that are commercially relevant. So we take leading edge compound semiconductor technologies, often made in high mix, low volume foundries, but we turn this into commercially relevant cost and volume chips, right? So each 3-5 wafer is used to simply produce chiplets. And obviously this is straightforward, right? The smaller the chiplets, the more we make per wafer, the lower the cost. But I wanted to give you a number to take away, which would be our chiplets are roughly 250 by 250 microns. And depending on the technology, depending on the volume, you're talking about chiplets that can be anywhere from 10 cents to $1, right? So very, very low cost. And usually you may have a few of them per chip, but that's really the value from a manufacturing cost model here. So once we have those chiplets, well, we have to integrate them into our silicon platform. It looks like silicon, it tastes like silicon, it smells like silicon, right? 90% of the wafer is still silicon, but now we have these little chiplets embedded in the wafer. And I'll go over how we do this in a second. But this is our manufacturing IP, right? And the idea is to develop the best performance RFICs at the lowest cost and with the most intelligence on chip. So what does a cross-section look like? So this is a cartoon. We do have cross-section images, but I didn't use them here. Effectively, the pseudolithic process is a reconstructed wafer with embedded 3-5 transistor chiplets into the silicon. We start by taking our silicon wafers from our foundry and etching through substrate vias or through substrate cavities all the way from top to bottom, creating effectively a Swiss cheese wafer, if you will, with pockets into which we embed our chiplets using a dielectric sidewall bonding process. So it's represented on this cartoon with the black area. The advantage of the dielectric bonding process is that it's very low cost, it's low parasitics at RF, and it allows us to run interconnects on the top directly from the chiplets to the silicon to electrically stitch the whole circuit together. So we have a wafer level process with gaps that can be as narrow as 5 microns using an effectively redistribution layer type fabrication to interconnect the silicon interposer or silicon CMOS wafers with the chiplets. On the backside, we add a thermal backplane through a sputter and plating process, just like one would do in a MMIC level technology with the backside gold, for example, just to provide DC and RF ground as well as thermal management solutions as we interface to the package. And then we can mix and match technologies, right? What you'll see later on is that we really use one integration process for any chiplets, any supplier we get, or any chiplet technologies. And so we have the ability to mix and match thicknesses, as well as interface on the front side, despite the different backend technologies used in the 3-5 suppliers. Maybe you know that some of them may use a BCB encapsulation or an air bridge interconnect, for example, in gold. Just to give you a little more details on the backend layers on the silicon are 4 layers. That's 2 thick copper and 2 aluminum layers. When we do the CMOS version, we have the ability to have 5 more layers as well. And so does this work at RF? Yes, this RF-SOI technology is actually very well suited for RF. This is an example of a transmission line built on the silicon RF-SOI technology, and it measures at 75 gigahertz, about 0.6 dB per millimeter. So this might be, 0.1 to 0.2 dB higher than what you can do with gold on silicon carbide, but still very, very well suited for RF high-performance circuit designs. This is all done through automation, right? We are not handpicking the chiplets and bonding them into the wafer. So I wanted to really allude to this in this slide. So we take the 4-inch 3-5 wafer from our 3-5 suppliers, and we effectively singulate those through a variety of techniques to create these microscopic chiplets. We end up storing those on the shelf as a standardized digital and physical library that we have and ready to go for prototyping. The silicon CMOS wafers today are core down. We are not yet processing at 200 millimeter, though that is very much on the roadmap. So we core those down into smaller coupons or smaller wafers to be able to process them at a shared facility. And we create the cavities and do the reconstruction of the wafer followed by the interconnect. So we're able to mix and match different technologies again. So I'm just showing one 4-inch source wafer, but we have a library of technologies, both from indium phosphide to gallium nitride and gallium arsenide available to take from. So how does this drive up quantities too, right? So a very interesting concept here when we talk about accessing leading edge gallium nitride and indium phosphide technology in these high mix, low volume foundries. Why would this be commercially relevant? Well, today in our approach, so in a traditional MMIC approach, one such foundry may produce X wafers per month, and that will turn into, tens of MMIC or hundreds of MMIC per wafer. With our approach that is a lot more manufacturing efficient, we now have 100x the number of transistors per source wafer. So with the same input of the III-V foundry, we can yield a lot more products. That's because about 10% of the transistor chiplets are used into the silicon 200 millimeter wafer. So just to give you an order of magnitude, we might yield, north of 50 to 80,000 chiplets per 4-inch wafers. We would use about 15,000 of those if it was a single technology integration into a 200 millimeter wafer. So the production output per III-V wafer is significantly higher, which speaks to our manufacturing efficiency, which speaks to our model of accessing those leading edge foundry towards commercial applications. And we can do this at lower cycle time and lower cost than monolithic solutions. One of the reasons is we can really increase yield, right? So the passive yield on compound semiconductor wafers is usually one of the bottlenecks to yield high performance complex design mimics. With silicon, that's not the case. So I picked one of the 10 key parameters that we're tracking from our silicon supplier. This is a sheet resistance for one of the metal layers. And what you're looking at is a sheet resistance on the y-axis on the left-hand side here in million per square as a function of just number of wafers effectively that we've received from our vendor. And what you can see is very, very tight spec around the sheet resistance. This is true for all key parameters. The yield is effectively 100% through those foundries, right? So very, very high yield. The second aspect that has been a great surprise to us as we started to do this was that the transistor performance and the transistor yield has also gone up through our III-V suppliers, because now they only have to repeat the same device all over the wafer. And we see a lot more consistency within wafer and across wafers for key process specs. So here I took one of our commercial GaN supplier on resistance data. And what you can see is across a series of wafers, the CPK is really high for this on resistance, both in wafer and across lot. So these are very exciting results, and it speaks to obviously our approach to using a supplier at what they do best, which are making transistors in III-V and doing high yield multi-layer interconnects and CMOS platform in the CMOS platform. So now that we have all this, this gives us the ability to prototype very quickly. We've had instances where we went from design to test in 3 months. We've had instances where we received chiplets from our supplier, and then by the end of the week, we had circuit data in a pseudolithic amplifier solution. So building this library is critical for us as we prototype with different technologies. And today we effectively have multiple technologies, multiple blocks on the chiplets sitting on the shelf and ready to be used into a variety of circuits from 6 to 86 gigahertz effectively. So we are able to explore thousands of different circuit topologies across multiple frequency bands, sometimes on the same wafer, right? So this allows you to go and explore in parallel really multiple design technologies and architectures and transistors using the same silicon tape out runs. Obviously, as I mentioned, today we are not fully standalone in our integration process, and so I wanted to highlight obviously how we take advantage of the resources we have access to and show you our roadmap. So I think I've convinced you by now that we truly value the partnerships we've developed with our suppliers, both on the III-V wafer side and the silicon CMOS wafers. And we plan to continue to outsource these steps, right? We don't want to be in the business of making transistors, and we want to continue to work with those foundries to deliver the best wafer and the highest performance. The pseudolithic integration process today is done in a mix of facilities. So we use a couple of vendors specifically, for example, for dicing or chiplets. We own captive tools at Pseudolithic that we cannot access through shared facilities or that we want to maintain as a proprietary step that specifically around the reconstituted wafer technologies that we've developed. And then we access a lot of the shared tools at the NanoFab at UCSB and at the NCF clean room in the CNSI at UCSB, mostly to do what I would consider more traditional processing steps, such as photolithography, etching, and deposition metallization steps, for example. We do have a couple of those tools that we own set up in the CNSI clean room, specifically around plating and etching. Then we do wafer test at Pseudolithic and outsource packaging and PC board assembly and test again back at Pseudolithic. So hopefully that gives you an idea of how we take advantage of local resources to turn our wafers around very quickly. So now let me transition to the pseudolithic design flow. This is fairly top level. Jim would be the expert and his team obviously in this context, but I wanted to give you a little bit of flavor of how we do this today. So we've got this chiplet design, right? This is another example. You probably cannot see the details here, but we have a mix of single-ended designs, differential designs, some chiplets with stabilization networks, some chiplets that only have transistors on them and pads effectively. But we've built a standardized library of those chiplets. Those today are typically, watt to multi-watt class level chiplets, and really trying to be as compact and as small as possible to benefit from our integration process. In part, as soon as the designers understand the product specifications that we're trying to get, he or she takes those chiplet designs, develop the interconnect process and the schematics around the circuit design. This is pretty unique in the sense that, again, it's a mix and match of technologies, and we're able to EM the whole circuit architecture, do design rule check and LVS and so on, all at once. And the output today is obviously the CMOS wafer design that we send to our foundry, and then the pseudolithic mask set that we use to integrate the chips and develop the interconnects on top of it. Our EDA environment, as you can imagine, is also hybrid between several EDA companies. I've listed out sort of the process flow today, from the foundry PDKs and the transistor models to setting up the layout, designing the interposer, doing our verification, packaging and thermal analysis. And we mostly rely on Keysight ADS and Cadence tools today, as we mix and match between 3.5 foundries and 3.5 models with, again, a silicon design platform.
Florian, there are a few questions in the chat. Do you
Yeah.
want to pause from them now, or do you want to come back
That
to
would
them?
be great. I'd love to.
Okay, one
How
of
do you want
them
me to do this?
one of them was about 10 minutes ago, so I'm sorry we're a little late to catching that one. But the question is, the RF performance of CMOS technology is going to drop while the 3.5 devices have large threshold voltage. Process variation can't cover all RF circuit blocks, such as analog beamformer IC. How can you solve the problem using heterogeneous integration technology?
That's a great question. So, part of the CMOS intelligence we're building in is to be able to address these threshold voltage variations at the chip level per each chip, doing this in large format arrays. So we really think the being able to intimately integrate the CMOS biasing and power management and control with 3.5 transistors will significantly help to address this type of shifts. Secondly, again, if it's the uniformity goes up by only fabricated transistors, right? So there is still drifts with temperature, for example, or with other type of stresses, but much less through the fabrication process.
Thank you. And then three more that were more recent. The first is there live test data on the PLIC showing KPOH differences between the process qual and the resulting PLIC? And I skipped one, but you can answer that one and then we'll go to the next one.
Yeah, so we are starting, obviously, we are building quantities and we are building reliability data. I think I have a couple of slides on this in a minute. Maybe the downside of our approach today is that we haven't had to do many chiplet tapeouts, right? Because each tapeout feeds a lot of circuit design innovation. We haven't explored some of the manufacturing KPIs that could happen when you increase volume. So corner models are, something from a manufacturing standpoint, something we have not been able to explore just yet.
Thank you. And then the one before that was, is there a way to rework chiplet sites if the overall chips test is bad, or do you scrap the whole chip?
Yeah, good question. And actually, I don't have a slide on this. Today we would scrap, right? I think the value though is the known good die, unknown good die, tested die, etc. We strongly believe that the visual inspection is sufficient coupled with wafer level PCM data. And so again, it's back to the cost value of this chiplet in our integration, right? Because they are now so low, it's easier to test at final a full circuit and scrap what doesn't yield rather than pre-test and pre-screen everything. Secondly, again, I think this idea of the CMOS intelligence and the brain on the chip is to be able to adjust performance shift across across a large volume of chips of the same design and being able to tune each individually to perform the same, right? So there is a knob that we can use now to improve yield again. So functional yield versus, good or bad, right?
Thank you. There are three more questions. They're accumulating faster than we're answering. Do you want to keep going with questions, or do you want to get through some more slides and come back to the questions? It's up to you.
Yeah, let me give I'll take a subset of the next charts then and maybe try to finish early and answer some more questions later.
Okay, thanks for your patience, Barry and John. Go ahead, Florian.
Yeah, no, thank you for the great questions. I did want to just show this on the modeling side. A question we often get is, well, how does a pseudolithic wafer contrast or compare against GaN on silicon, right? Obviously, large foundries today are pushing RF GaN on silicon, not power, right? RF GaN, and have the whole ecosystem to develop low volume GaN. This is not GaN on CMOS, right? So right away, we believe we have an advantage is that we can bring CMOS next to GaN, and we can bring in phosphide and HBTs and so on. But just if you look at the transistor performance, so what we modeled here is a GaN pseudolithic chip with interconnects, with our dielectric bonding, etc., on a package, right? That's the left cross section and the 3D cartoon on the top. And we compared it against the same thickness wafer with a GaN transistor on silicon, right? And we applied different power levels across the 8-finger transistor cell and compared it. So the results are on the next slide. And what you see is, if you look at temperature on the y-axis as a function of dissipated power, both for the pseudolithic chip in blue and the GaN on silicon in orange, we achieve much lower junction temperature or peak temperature, up to 100 degrees C of difference when you dissipate only 10 watts across your chip, right? So very, very quickly, we are able to have better thermal performance. Why? Because we still rely on the performance of GaN on silicon carbide. Even though we do this in a hybrid solution, all of the heat flows straight down in this high thermal conductivity silicon carbide and into the package. The fact that we have a smaller chiplet or that we have a dielectric embedding around the chiplet does not deteriorate the performance of the native GaN on silicon carbide. And that's really a powerful statement and a testament to the high performance GaN on silicon carbide technologies that have been developed by several of those US leading edge 3500s. So, GaN on silicon is great, but there is a place for it and a place where GaN on SiC is still significantly better. Before I dive into some of our circuit results, I did want to highlight, obviously, other approaches, whether it's wafer bonding, flip chip, or microtransfer printing across several metrics, such as design flexibility, mix and match technologies, and how quickly one can access chiplets or transistors, thermal management, and prototyping cost. And we truly believe that across those four metrics, the pseudolithIC solution is the best for all. Obviously, microtransfer printing also gives significant, and flip chip gives significant design flexibilities, right? You can make small transistor chips and integrate them on a silicon CMOS this way with bumps. However, maybe the thermal management isn't quite as good, right? So microtransfer printing today, the chip would be sitting on the dielectrics from your backend solution, for example, while the flip chip would be facing up with bumps in between, right? So anyway, happy to discuss. Obviously, this is our view of the world, and I'm sure there is other views as well. So moving on, I have a series of slides here on examples. I'll go quickly through them, right? As I mentioned at the outset of the presentation, this is really just to give you an introduction and a flavor about the pseudolithIC technology. Yeah, we'll show you some of the good results we've had. We've also had circuits that don't work, they oscillate, they're unstable, etc. But that's part of the fun and part of developing our products. So I picked this one because that was the first prototype the team realized under the California Dreams ME Commons program we have that's managed by Northrop, and we are a subcontractor on this. We were able to gain access very early to the 90 nanometer GaN-HAM technology through what's called Sterinite. That's a program funded by Navy Crane to effectively democratize access to high-performance GaN through multi-project wafer runs, right? So we took advantage of it because it fits with our vision. The chiplets are differential designs here. It's roughly a 2-watt chiplet, and we achieved first-pass success. We just picked 2 samples here. They overlay very nicely onto each other, and that was a building block. And the first time we took again a 90 nanometer design, chipletized it, and then integrated into a passive silicon wafer here. Building on that, we developed a 2-stage design at Ka-band again, and achieving over 18 dB of peak gain, over 2 watts of output power, and efficiency of greater than 35% at the probe station, right? So measured with RF probes on the chuck with no extra cooling. Again, so 2 chiplets into a pseudolithIC wafer with a die size of about 1 by 2 millimeter. And yeah, excellent results, right? This starts to be fairly competitive at Ka-band with, in the 2-watt class amplifiers with high efficiency. What's unique, obviously, is we have on the long-term roadmap, a lot of the DC biasing and power management will be done in the CMOS platform, and therefore we can use different voltages at the gates in the final solution, while today, obviously, it's done with external power supply. We've taken that same technology and looked at switches. We have actually several switch technologies available today. In one of the other slides, you see a different example, but this works quite well. At 28 gigahertz, there's a 1.3 dB insertion loss, 25 dB isolation, so that would work well in a Ka-band TR module. Again, first-pass success on this design. You see visually the chip isn't perfect, and yet it still performs electrically very nicely. And I'll skim through those, but we've done indium phosphide HBTs, indium phosphide HAMs with 2 dB noise figure at Ka-band. and even building E-band LNA blocks. So this is what's unique about this one, or the takeaway in this slide is really about our ability to take the interposer passive technology to do first pass, low cost design innovation, and then export it directly into the CMOS platform, which is obviously a little more expensive and takes a little longer from our foundry supplier, but we can get very similar results without a redesign. The pseudolithic process is the same, whether you use a CMOS wafer or an interposer wafer, the chiplet process is the same, etc., etc. It's just the design blocks that are being able to be exported. So a very nice way to prototype at low cost and then transition to a more functional version with CMOS blocks once the designs are verified in the interposer, even up to E-band. And so now, that we've built those building blocks, we have the ability to really take advantage of the best device technologies to build more complex chips, right? Along with upgrading those with SPI interfaces, multiple channels on one die, etc., thanks to the high yield CMOS blocks and performance of the silicon processes. So as an example, this is something we've started to look at a couple of years ago, where we've built a HBT pre-driver at Ka-band and combined it with a GaN-amped output stage. The latest news here is subtle but very impactful for us. This is our first three-stage PA design. Again, it uses a HBT, a slightly different chiplet design, coupled with 2 stages of GaN. To achieve a 26 dB gain. This will be, we don't have power data here, but it's a 2-watt amplifier as well, and a very exciting result. Again, how we take advantage of mix and match, not only at the functional block level, but even within the amplifier design. Similarly, our TR chip complexity has increased, right? So if you remember the cover slide, we had this 3 chiplet design, one for the PA, one for the switch, one for the LNA. And today it's evolved into a 6 chiplet design with GaN, indium phosphide, and GaN on the switch. We yield this pretty routinely now and effectively focus on design optimization and performance of those TR solutions. So sure, it's obvious, but we have an input switch and output switch on this TR chip here, a 2-stage PA and a 2-stage LNA on the receive. I will point out the design in the middle because this was the first demonstration or the first instantiation of our CMOS SOI switch that is native to our CMOS platform. So effectively, it comes for free. This was also a Ka-band design, very high isolation and low essential loss. So very competitive RF block solution designed into the CMOS process, RF SOI process here. And then today we take some of those chips, right, and effectively build either evaluation boards or demos. This was a 4x1 phased array that the team set up in the lab. So please don't worry about the mess on the test bench here, but we measured the output power with a power sensor. There was a horn antenna on the receive, and then our array, which was powered by a silicon beamformer evaluation board and a DC control board on the edge. And I think, to no surprise, we measured a higher output power than the silicon-only solution, and we are continuing to work on optimizing both transmit and receive as well. I think the success there initially was that this was really the first time where we went from a digital beamformer or beamformer IC chip, integrated our chip on a wire bond and die attached on the board, and then the antenna design as well, all at Ka-band. There were a couple of questions earlier about yield and reliability. So this is some example. As I mentioned earlier, we have one process for all, right? So that's really the value. And we've tested hundreds of parts today. We typically exceed 80% yield. So not quite manufacturing yield, obviously, by any means, but enough that every wafer yield circuits that can be tested. And then similarly, early data on reliability have been very positive. I picked one of the reliability tests we've done, thermal cycling, using a mill standard across 3 different chiplet technologies, GaN, indium phosphide HAMT, and HBTs. And on this slide, you're seeing results after 1,000 cycles, which if you've not done it, this is several months at the third-party vendor where chips are mounted on a die attach carrier and cycled through their ovens, again, per mill standards. And what we show here is effectively no visual and electrical degradation after those 1,000 cycles. So very positive early results, much more work to do, obviously, as we increase the number of chiplets per chip, etc., but at least no showstopper in the short term. Let me try to conclude quickly a little bit on the CMOS capabilities. Maybe I'll just show a couple of slides on this, and then I'll go to the acknowledgement section so we can have time for questions. But the idea of bringing CMOS right on the GaN or the 3.5 level is really compelling, right? You can built-in self-test, reduce the cost of testing, reduce things like burn-in, and really improve the yield and operational lifetime of the chips. We can also integrate biasing and power management, which would typically require external monitoring and external circuits, which would increase the size of your phased array and the cost. Now, this can be done at the chip level. I've alluded to the fact that we're building RF signal blocks already and with the CMOS process, right? So we use it for mixers, attenuators, obviously sensors and so on, and even stages on our LNAs and PAs. And then signal processing, right? So obviously the idea of bringing all of those different IP blocks into a chip would greatly benefit if you could just have DACs and ADCs at the output. Maybe I'll just briefly mention this just to show you again in terms of where the complexity of our chips are at today. This is a E-band receiver chip. There is a 4-stage indium phosphide HEMT LNA with built-in attenuators coupled to a full CMOS receiver chain and an indium phosphide HBT chip as well. And we have the whole CMOS IQ down converter. So very exciting development. This takes multiple spins to really realize. This was the first generation. We have test data now, and we can build on that version to develop this low-cost, high-performance E-band receiver. So in summary, I hope I convinced you that HI is really critical for millimeter applications to build circuits, to build complex chips at the cost and volume of silicon while maintaining the performance of gallium nitride and indium phosphide. This intelligence piece is very exciting to mix and match compound semiconductors and interface them at high level with analog, digital, and RF circuits. With that, let me just quickly acknowledge a lot of people who have contributed to this effort so far, and obviously our company. So we've had a chance to have several SBR projects, as well as the California Dreams and Commons project as a subcontract to Northrop. And obviously, I'd like to thank the facilities and the people running the facilities at UCSB because we've done a lot of work there. With that, I'll take questions. Thank you.
Thank you very much, Florian. That was great. As we go to questions, I will say you made a comment about the lab setup and what it looked like. I've been to PseudolithIC, and I will say it's a great place to see lab to fab transition in action.
Thank you.
Live in one spot.
Thanks.
Florian, are you looking at the questions in the Q&A, or do you want me to read them off to you?
I can look now. Yes.
Okay.
So I see the question from Barry. Do you test the 3.5 chiplets before integrating to silicon stems? What's the yield at final test? So I think I've answered this a little bit. So we do wafer level testing of the chiplets of PCM structures. My apologies. So we do not test the chiplets electrically directly. We could. We just think for one, we don't want to have probe pad damage on our pads. For two, is we don't think it's necessary. We do a visual yield inspection, right? So they are visually screened, just not electrically. And then the yield at final test, again, depending on the circuit complexity, we have yield exceeding 80%. Some wafers have 100% yield, some wafers have lower yield. So it's still a work in progress. Question for John. If the scribe lines are 50 micron on a wafer, a large area is lost. Yes, excellent question. As you probably know, today there are ways to reduce scribe lines or dicing streets, right, through plasma dicing technologies, stealth dicing. Those are really being developed for silicon, but they work equally well for compound semiconductor, silicon carbide, and indium phosphide. So while today we are not actively using those, we have demonstrated the capabilities, and as we go, obviously, as we care about cost and yield more and more, I do think the technology exists today to minimize the street width and maximize the yield. And then Barry again, is there a sweet spot of number of 3-5 transistors per silicon stamp, considering each technology and application? I think my indirect answer will be that we try to use CMOS everywhere we can, right? The goal is to use the least chiplets we need per chip because it's cost, right? They cost more than the silicon per square millimeter. And obviously we have to integrate those, right? Is there a sweet spot? We don't know yet. I think we've shown that we can yield 6 chiplet designs. I think we have interest in exploring the co-integration of larger chips and smaller chiplets, or chips with higher chiplet numbers, for example. But we don't know the upper bound yet.
Thank you very much. Are there any other questions? I saw a hand up, but I think it went down. Oh, here's another one in the chat window from Chun Li. Thanks for the presentation. How does this novel integration approach compare to copper pillar in terms of performance and cost?
Yeah, great question. So I mentioned we can have gaps between our interconnects of 5 microns. That effectively is your bump pitch, if you will, right? So we are much closer to hybrid bonding in terms of pitch than copper pillars today in our integration process. So our chiplets are small because our pads are really small, right? The transistor area is very small too. We do believe that this effectively face-up approach is critical, right? We are able to dissipate heat through the backside very well because it's a through substrate approach, and so we have access to the backside of the chiplets directly. I think you are referring to a flip chip copper pillar. I think then you would have to address the thermals a little differently. So I think in terms of pitch and performance, thermal performance, we are at least equally as good, if not better.
Thank you. Any other questions? Looks like we are all set with questions. This nice webinar format shows us a count. You answered 7 questions and completed your seminar. So that was very good. It was a very interesting seminar. Thank you for all the good work you're doing, Florian.
Thank you.
You and your team. It's great work. We will now shift our attention toward looking over the next couple of weeks. Next week, we are not having a seminar in this series because we are hosting the Moses 2.0 Developer Workshop in Arlington, Virginia. Amy, we're seeing the presenter's slide instead of the slide view here, if you can switch. But
yeah, I'm trying to move it, sorry.
Okay, that's okay. So there's a QR code there, or contact Amy or me if you want to get an invitation and you don't already have it to the Moses 2.0 Developer Workshop next Friday in Arlington. That is the day after the IMAPS onshoring. I forgot exactly what their workshop is called, but if you're in town in Arlington for that workshop, you can stay one more day and join us at the Westin in Arlington. We also have a QR code for the seminar series. we've got another question. So let's Florian, if you're still ready to answer questions while we're displaying what's on the screen. Amy, you can go to the next slide, and Florian, you can answer the question if you're willing to use some form of adaptive patterning to account for placement inaccuracies.
Yeah, great question. Not today. I think we've designed our chiplets and our cavities and our interconnects to be compatible with the speed and accuracy of our integration process. Obviously, as you know, Andrew, companies like Deca have commercialized adaptive patterning technologies and have been able to use higher bonding throughput tools, right, as a result. So obviously something that could be on the roadmap, but not something that we need today. Some of that is because the RF dimensions are not so small that you can't really design into it versus, maybe digital, very high I/O type bonding techniques.
Thank you. You can see on the screen now our schedule, which has some slots to be filled. If any of you are interested in offering to give a seminar, please contact Amy, me, or Ajay Jacob. And the slide before this, I don't know if we're going to see it or not, but the QR code to register for our seminar series so you can get notifications. So with that, I will thank everybody for attending. We had a great turnout today, and thanks once more to Florian for the great seminar and for your contributions to the ecosystem nationally, internationally, and in the hub.
Thank you, Steve. Thank you,
Thank
everybody.
you. Bye, everybody.